So now we will use equilibrium expression to solve problems. So take a look at this reaction. The substance cis-silbene will transform of that substance, and the Kc for this reaction, which will reach the equilibrium, is 24.0. So we want to find out what are the equilibrium expression for this substance. So let's say that we have, so we have to write down the equation, cis forming transform, and then we will put together a table. Initial concentration, molarity, change in a concentration, of course, molarity, and the equilibrium concentration, or we call it ICE table, ICE table, ICE table. Concentration, change over concentration, equilibrium concentration. So let's say the initial concentration of the reactant is 0.85. And at the beginning, we don't have a product, and initial concentration of a product is 0. So since we have no product, we know the reaction has to go from left to right to make product. So that means this substance reactant will be consumed minus, let's say, some amount X, minus some amount X of the reactant, and we will be making a product plus X. At equilibrium now, we have to add those two together. We will get 0.85 minus X. That's the equilibrium concentration of the reactants. And the equilibrium concentration of the product is just X. For this reaction, we have to write down its Kc expression, products over the reactant. And then we can substitute everything that we know. We know that the Kc is 24.0. The product is X at equilibrium concentration, and the reactant is 0.85 minus X. So when we will solve this equation, algebraic equation, we will find that X equals to 0.816 molar. So that means at equilibrium, the concentration of the product, which is X, will be 0.186. And you also can find equilibrium concentration of the reactant. You just have to take 0.85 minus 0.816. And that's what we have. So, and then we can double check. We will take the equilibrium concentrations of a product and the reactant. We will divide them, and we'll see that the Kc is 24, and that is correct. So we solved the problem correctly. So we are using this ICE table, ICE, initial change equilibrium, to find all sorts of things. We can find the Kc, we can find equilibrium concentration of the product, equilibrium concentration of the reactant. So let's take a look at this sample problem. So they gave us the reaction, and they say the Kc for this reaction is 54.3 at 430 degrees Celsius. What will the concentration be at equilibrium if we start with 0.24 molar concentration of both H2 and I2? And they wanted to know what the concentration will be at equilibrium. So this is what we do. First, we will write the reaction. This is our reaction. Then we are putting together the table, initial, change, equilibrium, concentration, ICE. The problem gave us initial concentration of hydrogen 0.24, initial concentration of I2 0.24, and we do not have initially a product HI, so it is 0. Since this is 0, we know that the reaction has to proceed to the right to make HI. So that means this will be plus, but those two reactant has to be consumed, minus, minus. So let's say it's a minus x. So this is a minus x. This is a minus x. But this is a plus. And why it's a 2x? Because the coefficient of hi is 2. So that's why it will be plus 2x. Then we'll combine those two terms together to find the equilibrium concentration. Combining those two together, and this is 2x. Then we're writing the Kc expression using this reaction, substituting everything which is given to us. And then we have to solve this equation in terms of the x and find the x. So x is equal 0.189. But equilibrium concentration of a product is a 2x. So that's why I have to take this value and multiply by 2. And I will find out what is the equilibrium concentration of the product is. And the concentration of each reactant is 0.24 minus the x. And that's what we are finding them. So this is also a similar problem. So you can follow this reaction and see how to solve this problem. Again, we're constructing the ICE table. Sometimes when we're constructing the table, we have to use the quadratic equation to find the x, but when the magnitude of decay, either Kc or Kp is very small, then the equilibrium problem can be simplified and we don't have to necessarily use quadratic equation. So take a look at this example, 15.10. This is the reaction. They said the Kc for this reaction at 205 degrees Celsius is 3.39 times 10 to the minus 13. They wanted to determine the value, the concentration of atomic iodine. This is the atomic iodine. This is a molecular iodine. This is the atomic iodine. When 1 liter vessel originally charged with this moles of molecular iodine at the temperature and allowed to reach the equilibrium. So they gave us the molecular iodine, they gave us the moles, and they gave us the volume. So mole over the volume, we can find the concentration. This is the initial concentration, 0.00155. Why? Because that many moles were dividing by 1. And initially, the atomic iodine is not present, it is 0. And the Kc is given to us. I do believe it's a typo. Either one of those, either minus 13 or minus 12 is a typo. Let's not pay attention to that. So we will put the equation. This is the reaction. Then we'll write down ICE table, initial concentration of molecular iodine. Atomic iodine is 0. This has to be consumed minus. This has to be formed plus. If this is x, this should be 2x. And we find the equilibrium concentration by combine them. So this is Kc, which is very small. And it's equal to 2x. This is the concentration. The concentration of the iodine at equilibrium, which is 2x. You have to also raise it to the power of 2. And the concentration of I2 at equilibrium is, this is the expression. Since the Kc is very small, 10 to the negative 12, we can say that the reaction did not really proceed that much to make products. Not that much of the reactant was consumed. And this expression minus x is really, really small. And it's literally almost equal to that initial concentration because change is not that large. How do we know that change is not large? We're looking at the Kc. Kc is very, very small. So that means not a lot of reactant converted to make a product. So this expression equals almost to the initial concentration. Then we can substitute this. Instead of minus x, we just will put this expression and we will find the x. And this is the x. Do you see the x is 10 to the minus 8? Very, very small amount of molecular iodine really converted to the atomic iodine. And also we can find the equilibrium concentration of both reactants and products. So how can we solve problems for the equilibrium concentration? First, we have to construct the table, equilibrium table, and fill in the initial concentration, including any that are zero. Then use initial concentration to calculate the reaction quotient Q, compare Q with the K, and determine if which direction the reaction will proceed to reach the equilibrium. Then define X as the amount of a particular species consumed, and use the stoichiometry of the reaction to define the amount of the other species consumed or produced. For each species, add the change in the concentration to the initial concentration to get the equilibrium concentration, then solve it for the X, and then calculate using this value of X, determine the equilibrium concentration of all the species. And then you can check your work, take all the equilibrium concentrations, divide them, and see if you can find Kc the same. So this is a sample problem. Also, please follow. Make sure you understand the procedure and how you have to proceed solving those problems. So this is the section which talks about when the reaction at equilibrium, what factors can disturb the equilibrium. So there are several things we can do to disturb the equilibrium. We can add or remove a substance. We can change the volume or pressure, change the temperature, or introduce a catalyst. We have something which is called Le Chatelier's principle, which states that when a stress is applied to a system at equilibrium, the system will respond, meaning the system wants to go back to the equilibrium. The system will respond by shifting in a direction that will minimize the effect of the stress applied to the system. So in this context, stress is one of the following. The stress can be if we will add or remove, add a reactant or product, remove a reactant or product, change the volume of the system, resulting in a change in the concentration or partial pressure if it's a gases, and we can change the temperature. Shifting refers to occurrence of either the forward or reverse reaction, such that the effect of the stress is partially offset at the system as the system reestablishes equilibrium. Shifting means that when the factors or the stress is applied to the system at equilibrium, the equilibrium is disturbed. The reaction is not an equilibrium anymore, but the system wants to go back to equilibrium. So it will do a necessary change and it will shift either to go to the product side to reestablish equilibrium, or will it go to the reactant side, shift to the reactant side and establish the equilibrium. So this is the first case is addition or removal of a substance. So take a look at this reaction. This is a Haber process, formation of the ammonia gas. They give us the concentration of all the species. We will write down the QC expression, substitute them with the values given, and we will find the QC equals to 0.297, which is equal to the Kc. That means those concentrations are at equilibrium concentrations, and our reaction is already at equilibrium. When the reaction is at equilibrium, the rate of the forward reaction equals to the rate of the reverse reaction. At that point, the concentrations of the substances will not change. They will stay that, what we have here, and they will not increase or decrease. Although it's a dynamic equilibrium, reaction still persists forward and reverse, but there is no changes in those concentrations. So let's say we are disturbing the equilibrium, we're applying a stress. So what we will do, we will increase the concentration of N2. So it was 205. Now we will change it to 3.51. So we really are increasing the concentration. So if I will take and put this new concentration of N2 into this equilibrium expression, we will see that the QC equals to 0.173, which is not equal to Kc. Our reaction is no longer at equilibrium. Stress applied to the system, and the reaction is not at equilibrium. Q is less than K, so the reaction will proceed to the right to achieve the equilibrium. An equilibrium that is stressed in such a way that the Q became less than K, the reaction will shift to the right to reestablish the equilibrium. So you see Q is less. So that means you have the reaction will move to the product side. It will make more product. It will make more product now, and it will reestablish equilibrium. And likewise, an equilibrium that is stressed in such a way that Q becomes greater than K, then the equilibrium will shift to the left to reestablish the equilibrium. So once again, if I am adding N2, the reaction has to go to the right. To decrease that, I am adding it, so it will actually decrease that, and it will consume N2 and go to make more product. And if I am taking this out, if I'm taking N2 out, then the reaction will go to the left to make more N2. So that's the Le Chatelier principle. So please make sure you will follow all of those changes happen to equilibrium. If I am adding O2, removing H2S, removing H2O, adding sulfur, what will happen to the equilibrium? I just wanted you to pay attention to the D, addition of S, sulfur, solid. Take a look at D. When we are adding sulfur, there will be no change at equilibrium, because do not forget, solid and liquids, they're not part of the equilibrium expression, and they will not affect the equilibrium. So when I'm adding oxygen, the reaction will shift to the right. When I'm removing H2O, H2S, I'm taking H2S out, the reaction will shift to the left to make more H2S. If I am removing H2O, the reaction will go to the right to make more of that. But if I'm adding sulfur, solid, no change, because solid and liquids are not part of the expression. When you have a reaction, all the substances are in a gas phase, like in this one, they, let's say, giving you the concentrations of those substances, and you will put this in the QC expression. You'll say that the QC is 9.31 times 10 to the negative 3, and this is greater than Kc. So what will happen if, this is the substances. So what will happen here? Do you see this is all the reactants and the products in the one vessel. So what will happen if we will increase the pressure here? We're increasing the pressure. As we increase the pressure, the volume becomes smaller. You see, this is the volume before I change the pressure. Once I increase the pressure, the volume decrease. So in general, a decrease in volume of a reaction vessel will cause a shift in equilibrium in a direction that minimizes the total number of moles of a gas. And if I increase the volume, it will go to the side with the more maximized total number of the mole of the gas. So take a look at this one. So this is this is 1 mole of a gas, this is 2 moles of a gas. When I increase the pressure, the volume becomes smaller. The volume becomes smaller, the reaction will go to the left side where you have less molecules of a substance. So the reaction will proceed increasing pressure, which will decrease the volume. The reaction will proceed to the side with a less number of molecules. But if the volume is increased, then the reaction will proceed to the side with a greater number of molecules too. So for this problem, they're asking for each reaction predict in what direction the equilibrium will shift when the volume of a reaction vessel is decreased. Well, first of all, they have to be in a gas phase. This is gas, this is gas, this is gas. You have 1 mole of a gas on the reactant side, you have 2 moles of a gas on the product side. So when you are volume is decreased, the reaction has to proceed to the side with a fewer number of molecules. Fewer number of molecules is the reactant side. So in here, the solids are not part of the equation. The only part of the equations are 3 oxygen gas and 2 SO2 gas. So we are decreasing the volume. The reaction has to proceed to the side with a few number of molecules. So you only count moles of gas. Do not look at the moles of solids. So they're explaining 1 mole of a gas here, 2 moles of a gas on the product side. For the B, 3 moles of a gas on the reactant side, 2 moles of a gas on the product side. And for the C, you have 2 moles of the reactant and the 2 moles of a product. So for the A, 1 mole of a gas on the reactant side, 2 moles of a gas on the product side, shift to the left where there is less moles. For the B, less moles are on the product side, the reaction will shift to the right. For the next one, 2 moles on each side, there will be no shift. So when we're changing the concentration of the substances or volume, we will not going to change the value of the Kc or Kp. Only when we change the temperature, the value of the Kc or Kp will change. Make sure you do understand this.